Most people think uranium is extremely rare. It is not. In soil, there is actually more uranium than silver, more than gold. So then, why can only a few countries actually use it? That answer is uranium enrichment. And honestly, it is one of the most fascinating things I have come across. Let's get into it. Natural uranium has 3 isotopes, but the one that matters most is uranium-235. Here's the problem. In natural uranium, only 0.7% is uranium-235. The rest, 99.3%, is uranium-238. And uranium-238? Almost useless for producing nuclear energy. So the goal of enrichment is simple. Increase the percentage of uranium-235. But here is where it gets really difficult. Uranium-235 and uranium-238 are not different elements. They are isotopes of the same element. Same chemical properties, almost identical behavior. The only difference is mass, and that difference is incredibly small. Engineers have to use that tiny mass difference to pull them apart. That is the entire challenge. Before any separation can happen, uranium ore is processed into a yellow powder called yellowcake, then converted into uranium hexafluoride, UF6. Why UF6? Because it turns into gas easily, and gas is much easier to work with for separation. The older method is called gaseous diffusion. UF6 gas is pushed through barriers full of microscopic holes. The lighter uranium-235 molecules pass through slightly faster, but only slightly. So the process has to repeat hundreds of times, and each repetition consumes enormous amounts of electricity. That's why this method was eventually replaced. So, what replaced it? The replacement was the gas centrifuge, and this one is clever. UF6 gas spins inside a cylinder at incredibly high speed. The heavier uranium-238 gets pushed to the outer wall. The lighter uranium-235 stays closer to the center. That slightly richer gas gets collected and sent to the next centrifuge. Then the next, then the next. This connected system is called a cascade. Each stage, slightly more uranium-235, far less electricity than gaseous diffusion. This is now the main method used worldwide. There is also laser enrichment, where precise lasers target and separate uranium-235 directly. Sounds almost too easy. But the technology is still under development, not yet used commercially. So, if the science is known, why can't every country just build one? Because knowing the science and building a working machine are completely different things. A centrifuge has to spin at tens of thousands of revolutions per minute, perfectly balanced, almost zero vibration. Any small defect, and it fails. Advanced materials, precision engineering, specialized equipment, controlled facilities. This is not something you build in a garage. The enrichment level needed depends on the use. For nuclear power plants, 3 to 5%, although some reactor designs can use natural uranium with no enrichment at all. For highly enriched uranium, 20% or more. Naval reactors? Classified. Different for every country. Finally, weapon-grade uranium, around 90%. And the challenge was never finding uranium. The challenge is separating 2 almost identical isotopes using a difference in mass so small, most instruments can barely detect it. And that is exactly why only a few countries can do it. Hey, this is Peak of Science. If this video made you think, hit subscribe. See you in the next video.